All right, everyone, welcome. In today's video, we want to cover power series. So we're going to introduce the notion of a power series. Power series are going to be what we look at for the rest of this unit, and they're really kind of the capstone of Calculus 2. Even though it's not our last unit, it's probably the most important part. This is the part, and if you're a BC student, this is the part that you really want to take home. So we kind of covered for the first part of the unit, we covered what a series is, what a sequence is. Then we also covered all those tests for divergence. Now we're in the third part where we're going to cover power series, which is really the application of everything we have just learned, and in particular, an application of the ratio test. So let's get started. So the definition of a power series centered at some x value a, so this is x equals a, is of the form the sum from n equals 0 to infinity of c sub n times x minus a to the power of n. And so if we multiply all of this out, we can converge for some x here, to a function such that our function is equal to the series. So basically what we're saying is that for some values of x where our series converges, our series is actually going to be equal to a sum. So it would be a sum from n equals 0 to infinity of this general formula c sub n times x minus a to the power of n. Now this is really interesting because this is a great way that we can approximate functions. We're going to get into that later. But let's do a couple of examples just for our first video on this topic. So here's an example. Where does the series converge? So this is really the root of our problems for this first video, where series converge. So now that we have this extra thing in here, we're adding x and n into the mix. So we have two variables that we want to look at. N is our index. So the series we are looking at is the sum from n equals 0 to infinity of x to the n times n factorial. Okay, now we're going to use the ratio test to prove whether the series converges or diverges. So we take a to the n plus 1 over a to the n, absolute value. We don't really need the absolute value because these are all positive. So that's x to the n plus 1 times n plus 1 factorial over x to the n times n factorial. And this is equal to n plus 1 to the x power. Now, if we take the limit of this, this is going to go to infinity. As this gets arbitrarily large, this is going to dominate even this term here, even if this is arbitrarily large, because we have the n plus 1. So no matter what we choose our x to be, as n goes to infinity, everything's going to go to infinity. So the series converges for everything unless if x is equal to 0. If x is equal to 0, then this whole thing equals 0, but that doesn't help us all that much. All right, let's do another one. So where does this series converge? We have the sum from n equals 1 to infinity of x minus 2 to the nth power over n. Okay, so now we can look a little bit more into this. So we're going to use the ratio test once again. We take the sum, or we take the absolute value of a sub n plus 1 over a sub n, and we get absolute value of x minus 2 to the n plus 1 over n plus 1 times n over x minus 2 to the nth power. Okay, so we can cancel out a lot of these. We cancel out this there, and we cancel out all of this there. Then we can cancel out n's later on, and what we are going to get, if we simplify, is 1 over 1 plus n, or 1 plus 1 over n, times the absolute value of x minus 2. So now when we take the limit as n approaches infinity, we are actually going to see that that we go to 0 because we are getting to 1 plus 1 over n, and then we can decide what x values we will allow for a series to converge. So as we covered in the last, or 2 videos ago, we said that the ratio test concludes that a series is convergent when the limit is less than 1. So we need to assert that it's less than 1. So we assert that this part here is less than 1 for it to converge. So now we have this absolute value expression. So we get x minus 2 absolute value is less than 1. So now we need to have positive and negative cases. So we get negative 1 is less than x minus 2 is less than 1, so we add 2 to both sides. So we get that x is between 1 and 3. So now for x between 1 and 3, this series will converge. All right, let's do a final example. So we're actually going to look at the Bessel function now. So the Bessel function is a function used a lot in engineering and physics. It's very good for approximating things and solving integrals. But this is really one of the first word problems that we've had in a very long time. So determine the domain of the 0th order Bessel function. That takes the form j0 of x is equal to the sum from n equals 0 to infinity of negative 1 to the n, x to the 2n over 2 to the 2n times n factorial squared. Okay, so again, we're going to use the ratio test. The ratio test is always what we're going to use, just because of how helpful it is in asserting our range of where a function is able to be expressed. So we take this absolute value, we get a whole mess in here. Absolute value of negative 1 to the n plus 1, x to the 2 times n plus 1 over 2 to the 2 times n plus 1 times n plus 1 factorial squared times 2 to the 2n n factorial squared over negative 1 to the n x to the 2n. Okay, so we can do a lot of simplification. These guys are going to go away because of our absolute value. Well, and then we can also take care of some of the exponents as well as the factorials. What we are left with is x squared over 4 times n plus 1 squared. So now we can take a limit as n goes to infinity, and just because since we have this n plus 1 and then we square it, then we know that for any value of x, we are going to be good and our limit is going to be less than 1. So that is how we do that. This means that the series converges for all x, so the domain is all real numbers for j0 of x. So actually, we can approximate, or we can make an approximation that says that this is equal to this for all x. So we can approximate the whole thing for the whole function. All right, thanks for watching. We'll see you in the next video to talk about radius and interval of convergence, which is sort of what we just did. See you then.